Hello there, it's Ligaya from Boost Chemistry Revision, and welcome to this live revision session all about physical chemistry. So this is aimed at Year 13s, and we're basically going to be covering a few of the topics that I've already covered in previous live chemistry clinic revision sessions. So before we start, I'm just going to wait for maybe a few people to join, and so I just want to say welcome to everyone who's joining live and also who's watching the replay. If you don't know who I am, my name is Ligaya Batten. I'm a qualified and experienced chemistry teacher. I used to teach in schools in London and in Oxfordshire and Berkshire, both science and specialising in chemistry. Since then, I made the chemistry videos for a platform called My GCSE Science. So some of you who use that platform at GCSE might recognise my voice, but my face wasn't on the videos. So now, Dr. Owusu and I are running Boost Chemistry Revision, which is basically a website and revision resources, Instagram channel, and live revision sessions to help A-level chemistry students revise for obviously AS and A-level. In the next couple of months, we're also bringing on board biology and physics teachers. So hopefully if you're the kind of person who's doing all sciences at A-level, then keep up to date with what we're doing in the next few months, and you'll also see some new teachers in new subjects offering live revision sessions. Before I continue as well, I just wanted to remind you, if you haven't already subscribed, then please do consider subscribing to be updated on when we upload new videos and also when we're going to have new lives. This is actually the first time we've had the live completely public. Most of the time it's just only available to people who have already subscribed to the chemistry clinic. We've been doing it with a trial with a school in London, and it's been going pretty well with them. So Year 12 and Year 13s have separate sessions, and each week we study a different topic, going over key revision points, as well as going over exam questions, looking at exam technique and tips and tricks for answering exam questions. So this session is a mid-year review for physical chemistry, and on Sunday Dr. Owusu will be doing a mid-year review for organic chemistry, just to kind of help you to summarise everything you've learnt so far this year. I know some of you may have mocks coming up, and hopefully that will also help you to kind of kickstart your mock revision as well. So today we're going to be covering a few physical chemistry topics, equilibrium and Kc, acids, pH and buffers, lattice enthalpy and Born-Haber cycles, and entropy and free energy. We aren't going to be covering rates and rate orders and rate determining steps today, just because that's not a session we've already done so far. So that's actually going to be a live session that will be happening in a couple of weeks' time that will be focusing specifically on that topic. So that's just so you know what's coming up. If you would like to ask questions, please feel free to ask questions in the chat box, and I'll do my best to answer them as I see them and as we go. And also, if you like this, then you may be interested in joining up to the chemistry clinic, which is aimed at being a cheaper, more accessible version of tutoring. It's going to be £10 a month for the regular price, and that will give you access to weekly revision sessions on topics that will hopefully be parallel with things you've been studying at school. You'll be able to answer questions live, as well as communicate with the teachers through the platform anytime. And so definitely look out for that if you like this kind of live revision session format. As I said, in those sessions, we cover a specific topic each week and go over the main points, as well as look at exam questions and look at how to answer those exam questions. Any questions that you may have, please just let me know either in the YouTube comments or on my Instagram channel at Boost Revision, or also by email, ligai@boostrevision.com. All the details for everything are on the website, boostrevision.com, and thank you again for joining, and we'll get on with the revision stuff now. So if you bear with me, I'm going to share my screen. I've got the notes on my iPad. It should come up in just a second. So again, just a reminder that the stuff we're going to be covering today is really focused on what you should be learning, or what you would be learning in Year 13. So some of the stuff obviously is a continuation from what you would have learned at Year 12. So I'm just going to flick back to what we covered in the actual full live session. The stuff about dynamic equilibrium and the factors that affect equilibrium, that's sort of year 12 equilibrium stuff. So we're going to start with Kc, the equilibrium constant, which is kind of where you start off with equilibrium at A2 or year 13 level. So the equilibrium constant is a constant, obviously, that basically tells you the ratio of the reactants to products that you have in an equilibrium, in a dynamic equilibrium reaction. So just to make sure, you can see in the brackets here, we've got, this is for a homogeneous reaction. A homogeneous reaction means that all of the reactants and products in the reaction are in the same state. Actually, I'll write that down, same state. So this means they're all gases or they're all solutions. In theory, they could all be liquids or solids, but in reality, we don't really see that. So we're looking at writing an equation for the equilibrium constant when we're making sure that all of the reactants and products are in the same state. So it is possible to write Kc equations for heterogeneous reactions, but for that, you just need to make sure you're only including the terms that are gases or solutions, because liquids and solids actually can't be part of the equilibrium constant equation in this way. So this AABBCCDD thing here is sort of an example of the generic type of equilibrium reaction that you would normally see. The small letters, the A, little b, little c, little d, are supposed to represent the number of moles you have. So if this was a full normal equation, then this would be where you have like a big 2 to show that you have 2 moles of that substance in that equation. I'll change the color or change the highlighter. Yeah, so then this A and B, these are our reactants, and then this big C and big D are our products. So it's just important to know, like, that's how to kind of interpret the reaction equation in order to actually make the correct expression for Kc. So Kc then, as I said, is a ratio of the amount of, or concentrations of, products to reactants. So we've got the products in square brackets at the top, and the square brackets means the concentration of, so in this case, concentration of C and D, and that's in moles per decimeter cubed. And we've got the molar quantity up here at the top, showing that if you've got 2 moles or 3 moles of C, you've got to times, have that concentration of C to the power of however many moles you have. So that's important in terms of writing the expression. On the bottom, you've got the reactants. So again, same sort of thing, concentration of the reactants to the power of however many moles you have in the equation. So what does this mean? Maybe you can easily write this equation, you just put the products and the reactants together, but what does Kc actually mean? So as I've already mentioned, Kc is a ratio of the concentration of products to the concentration of reactants. Why is this interesting or important when we're looking at equilibrium reactions? Well, it gives us an idea of how far to the right or the left the equilibrium has been shifted, or where it is balanced, basically. If there are exactly the same amount of products and reactants in terms of molar quantities and concentrations, then Kc would be 1. So that's this first point here. If the concentration of products equals the concentration of reactants, then obviously the numerator on top of the equation would be the same as the denominator, and then you would have the same thing divided by the same thing, which always gives you 1. So if Kc is 1, that means that you've got an exact balance between the two sides of the equation. The forward and backward reaction happening at the same rate, that's already given equilibrium. But we're also saying that the concentrations of products and reactants are exactly the same, which is actually quite unusual. It's not normally the case. So if the products are greater than the reactants, that means that your C and D on the top is going to be a larger number than the concentrations on the bottom. And that means you're going to get a value of Kc that's further towards the right. sorry, I mean the equilibrium is shifted further towards the right. We've made more products, and that's going to give us a value of Kc that's greater than 1. So that's this bullet point here. So if there are more products than reactants, then equilibrium is shifted towards the right, and that means that the value of Kc is greater than 1. And usually if you see this, it'll actually be much greater than 1, because often equilibrium reactions are shifted heavily towards one direction or the other. And then finally, if products are less than reactants, so if if the forward reaction isn't really happening much at all, and this is really common in acids, then equilibrium will be shifted towards the left, and the value of Kc will be less than 1, usually something quite a lot less than 1, like 0.000 something, or 1 times 10 to the minus 3 or 4, something like that. So it's important to kind of have in the back of your mind what Kc actually means, rather than just looking at it as an arbitrary number, because it actually helps you to understand what's going on in the reaction and whether there are more reactants or more products in the reaction. In industrial situations, for example, trying to make ammonia, we want to make as much of the product as possible, and so we want to adjust the conditions to make sure that we've got an equilibrium shifted as far to the right as possible. And that's where you come into questions where you might have to discuss the different factors that affect the position of equilibrium. But for example, when we're talking about weak acids, you may remember that weak acids only partially dissociate, and actually there's a very small amount of acid molecules that break apart or dissociate into the positive and negative ions. So it's quite common to see a very, very small Kc, or in the case of acids, Ka, when we're looking at weak acids. So that kind of comes into talking about acids, pH, and buffers later on. Okay, so let's move on. An additional thing that you have to know in all of the specs is the fact that Kc is affected by temperature. So it's important to know at this bottom part here that Kc is not affected by concentration and pressure. Although you've learned that concentration and pressure can affect the position of equilibrium, that's usually a temporary effect where equilibrium is re-established and the same ratio of products to reactants will remain. So even if, for example, you add some extra A, so you've increased the concentration of A, yes, the equilibrium will shift to the right to kind of counteract that change according to Le Chatelier's principle, but overall, the reaction will rebalance and the new equilibrium will be established, which will have the same Kc. And the same thing happens for pressure. If you increase the pressure, you may remember from year 12 that that's going to push the equilibrium in the direction of the fewer moles of gas. But the reason it does that is to counteract the change in pressure and re-establish a new equilibrium with the pressure counteracted, and the products and reactants will remain the same ratio relation to each other, which means that Kc will not change. However, with temperature, temperature does change Kc, so it will shift the position of equilibrium in the direction of the exothermic or endothermic direction, depending on whether you've increased or decreased the temperature. And that will have a permanent effect on the position of equilibrium. So if the forward reaction is exothermic, then increasing the temperature will favour the backwards reaction, because increasing the temperature always favours the endothermic reaction. Equilibrium will therefore shift to the left, the concentration of the reactants will increase, and so if you go back to the Kc expression, that means that the value of Kc will get smaller. And then the opposite is true obviously for endothermic reactions, that's supposed to be a highlighter. Increasing the temperature will favour the forwards reaction in endothermic reactions, because increasing the temperature will always favour the endothermic reaction. So equilibrium will shift to the right, the concentration of products will increase, and Kc will get larger. So it's important to be able to express what will happen, not just to the position of equilibrium, but also to the value of Kc if you change the concentration, pressure, or temperature. And it's mainly important to know that concentration and pressure do not affect the value of Kc, but temperature does. So you'll also be expected to, as well as write the expression for Kc, you'll also be expected to calculate the value of Kc as well as calculate its units. So its units can change depending on what the expression is, because it's possible for the units of the concentration on the top and the bottom to completely cancel out, or for there to be more concentration units on the top or more on the bottom. So depending on your expression, the units are also going to be different. So it's important to calculate the value as well as the units when you're calculating the value of Kc. So in an example like this, we've been given an example reaction. PCl5 makes PCl3 and Cl2, and we've been given the concentrations at equilibrium of each of those chemicals. So we can just substitute that into the Kc expression, and then we get a value. At the bottom here, you can see to work out the units, we do the same kind of thing, but instead of substituting the value, we substitute the units in. So each of the concentrations will have moles per decimeter cubed. And if we have the same on the top and the bottom, we can cancel it out. So we can cancel out one each from the top and the bottom, and that leaves us with a unit of moles per decimeter cubed. So overall, that will give us a value of Kc, which is 0.011 moles per decimeter cubed. So maybe this seems straightforward, maybe you're still a bit confused by this, but unfortunately it's not always this simple. Usually questions will not just give you the concentrations of your reactants and products at equilibrium, and you're likely to have to calculate that from experimental data or other information. So this is an example of kind of what you need to do in order to do that. The Kc expression requires the concentrations of the reactants and products at equilibrium. Sometimes questions will give you the concentration at the beginning, or maybe the concentration of one of the products at the end, and you need to work out, well, how much of the reactant reacted, how much of the product will be there at the end, and you can work that out in terms of moles, but then you also have to then turn moles into concentrations. So even if you understand pretty well how to draw the expression and also have to substitute the values in and calculate the units, the hardest part is actually often calculating what's the concentration at equilibrium based on the experiment that has been done and in the question that you've got at hand. So in order to sort of help you to work to figure that, to get your head around that, just imagine, in this equation we've got PCl5 at the beginning, PCl3 and Cl2 at the end. So PCl5 is our reactant that we start with. So if we have a look, at this graph, the PCl5, the purple line, this is our moles of the reactant. And there's no product at the beginning. But then as the reaction takes place, the PCl5 concentration goes down because it's obviously being turned into the products, and the product concentrations will go up as it's being produced until it reaches a point where both of the reactions are happening at the same rate, and we have a constant, unchanging concentration remaining of both. So you're going to have certain concentrations at the beginning, and then a different concentration at equilibrium once equilibrium is established. And that's important to remember. So let's look at this question as an example. One second, I seem to be having a problem with the stream. Okay, I think it should be back to normal now. Okay, so we've been given the number of moles of phosphorus chloride. We've been told it's at 600 K. It's in a vessel that contains 5 decimeters cubed. So this is to help us to work out the concentration at the end. We've got a volume here. The equilibrium mixture is found to contain 0.08 moles of chlorine. That's our Cl2. So that's how much of the product has been made. Write the expression for Kc and calculate its value, including its units. So we have the initial moles of the PCl5, and we have the equilibrium moles of the chlorine. Because the equation is a 1-to-1 ratio, however many moles of chlorine are made is going to be the same amount of moles of PCl3 that's made. So this means that we can say that the equilibrium moles of both the chlorine and the PCl3 are going to be 0.08, and that's how much actually reacted in the reaction. And that's how we can work out how much of the PCl5 we've got left from what we started with. So again, one-to-one reaction, which means 0.08 moles. We have 0.08 moles of each thing. So that means that that's how much of the PCl5 reacted. We started off with 0.2 moles, 0.8 reacted, and so we take the amount that was reacted away from the amount we had at the beginning, and that gives us the amount we have at the end, or the amount we have at equilibrium, which is 0.12. Now this row here gives us, this row here now gives us the moles at equilibrium. And then before we can actually put that into the expression, we need to calculate a concentration. So moles equals concentration times volume. So concentration is going to be moles divided by volume. I think that's on the next page. Yeah, so basically here we've got the moles divided by the volume. The volume of the whole container is 5, so the volume of all of these is 5. They're all gases which fill up the container that they're in. So while it can be a bit confusing to think about the fact that we've got more than one gas in there, but they're all occupying the same space, that's actually what's happening. The only time we have to think about this differently is with some boards, you need to learn about something called KP, which is partial pressures, and then you're talking about the partial pressures of each of the gases rather than the overall pressure in the whole container. So the 5 decimeter cubed from the question is the concentration, or sorry, is the volume, and then we do the moles divided by the volume to get the concentration. So now our concentrations are down here, and we can plug that into our Kc expression to give us the answer 0.011 moles per decimeter cubed. Okay, I think we're going to move on from equilibrium now. The rest of this was exam questions and examples that we did in the actual chemistry clinic. So like I said, if you're interested in going through exam style questions and kind of getting tips and tricks on how to do those questions, then please consider joining our chemistry clinic. We're going to be officially launching it next week to everyone. So look out on Instagram and sign up for our email list on our website in order to be notified when you can sign up. Also, if you are watching this, then to be in with a chance of getting a free membership, then send us a screenshot by in Instagram, or share a screenshot on your story on Instagram. Send us a screenshot if your account is private so we can see you've done it, and you'll be in with a chance of winning a free membership for the rest of the year. More details on that to come. I'm going to be posting on the full details of that giveaway opportunity on Instagram in the next week or so prior to the launch. Okay, so we're going to go on to acids and buffers, which hopefully you'll see is actually related to equilibrium, because again, we're using a similar type of equation as Kc. We call it Ka, and it's basically Kc, but specifically for acids. So before we kind of jump straight to that, we're going to just look first of all at the kind of main thing that most people think about when we're thinking about this topic, and it's how to calculate pH. So we've got this standard equation for calculating pH. pH equals minus log of the concentration of H+ ions. So whatever we've got, if it's a strong acid, a strong base, a weak acid, or a buffer, we need to know the concentration of H+ ions in order to be able to calculate the pH of anything. Alternatively, we can calculate the concentration of H+ ions if we know the pH of something, and that's just by finding the inverse of this same equation. So the concentration of H+ is 10 to the minus pH. So you'd be expected to be able to calculate pH from hydrogen ion concentrations, or calculate hydrogen ion concentration for given pHs. And also, as we'll look at in the next couple of slides, you'd be expected to calculate pH even if you're not given the concentration of hydrogen ions, as long as you'll be able to work it out from the question, the information in the question. So this is just a kind of summary of the things we'll be going through in the next couple of slides. The ionic product of water is important if you want to calculate the pH of strong bases, because like we said, we want to find out the concentration of H+ ions, but a strong base has got lots of OH- ions. So we have to use the OH- ions in some sort of relationship there, which in this case is the ionic product of water, in order to find out what the concentration of H+ ions are. Then we've got this Ka equation, which is what we use to calculate the pH of weak acids. So hopefully you can see this is very similar to the Kc equation we were just looking at. We've got the ions, the dissociated ions, which are our products, on the top of the equation, and then we have our reactants, which is our weak acid, at the bottom of the equation. The reason we can call this Ka is because it's always going to be the same. It has the same kind of structure all the time, because the weak acid is always going to be breaking up into H plus and A minus. So this is Kc specifically for weak acids. And that's when you've got this bottom equation here, that the weak acid turns into, or is being dissociated into, the positive and negative ions, the acid and the alkali ions. Kind of just a reminder, sort of thinking back to Kc and the value of Kc, because this is weak acids and the dissociation is relatively small, we're going to have more of the products, or sorry, more of the reactants and less of the ions. And therefore the Kc for this kind of thing is always going to be less than 1, because the equilibrium is shifted quite far to the left. We only have a small amount of dissociation of the acid particles into the ions. So we always have a pretty small Kc, and that's just worth remembering, especially when you're calculating things that can help to kind of self-check and common sense check your answers. Okay, so just a kind of quick run through of examples of how you might calculate pH from this equation, different ways you would end up calculating the pH. So if it's a strong acid, I've got this one here, if it's a strong acid, then we pretty much can just take the concentration of hydrogen ions from the concentration of the acid. We can assume that those are going to be the same concentration because of the 1-to-1 ratio and the dissociation of ions. If you have a diprotic acid like sulfuric acid or a triprotic acid like phosphoric acid, then when you look at the balanced equation for the dissociation of the ions, what you'll find is you've got 2 hydrogen ions formed for every 1 molecule of acid. And so if you've got 1 molecule of acid, you're going to have 2 times the number of hydrogen ions when that has dissociated. So it's important to just remember that, because obviously sometimes they might give you that kind of an example, and just assuming that it's going to be the same amount of H plus ions to amount of acid is not going to always get you the right answer. But it is relatively straightforward. You just look at the concentration of the acid, figure out if it's the same or double or triple, and then just plug that into pH equals minus log H plus. It starts getting a bit more complicated when we're looking at strong bases. Oops, that's supposed to be a highlighter. Because strong bases will be giving us some kind of indication of concentration of OH minus ions. So, you know, concentration of NaOH, for example, will just give us, that will give us the concentration of OH minus ions. However, similarly as above, if you have something like calcium hydroxide, which has got 2 OH minus ions in the base, then that's going to dissociate into 2 OH minus ions, but you can still relatively directly get the concentration of OH minus ions directly from your alkali or your base. But in order to convert that into H plus ions to put into the pH equation, you need to use this ionic product of water equation. So Kw is a fixed number at room temperature, but it will change if you've got different temperatures. And Kw equals the concentration of hydrogen ions times the concentration of hydroxide ions. So if you know the concentration of hydroxide ions, you can rearrange this. You know that Kw equals 1 times 10 to the minus 14 at room temperature. You plug your OH minus ion concentration into the equation, and that will give you the H plus, which will then allow you to plug that into the pH calculation to find out the pH of strong bases. Again, another common sense check is obviously to remember that 7 is neutral, anything less than 7 is acidic, and anything greater than 7 is alkaline. And again, strong acids, sort of somewhere like 1, 2, and 3. Weak acids would be like 4, 5, and 6 in pH. Strong bases will be something like 10, 11, 12. maybe sorry, 11, 12, 13, and then the strong weak bases or weak alkylates would be sort of like 8, 9, 10. So just think about that when you're double checking your answers. Is that kind of what you expect? So for a strong base, you're expecting to get something like 12, 13, or 14. For a strong acid, you're looking for something like 1, maybe even 0.1, something like that. For weak acids, we use this equation, like I said, and in order to actually identify the value of the H plus ion concentration, we're just going to rearrange this equation to make H plus the subject, and that will give us H plus equals the square root of Ka times by the concentration of Aj, which is our acid. So with weak acids, we often will be given the concentration of the weak acid. And that we can assume that that is the same as the concentration of the ions that dissociate. And because we're breaking up the weak acid into 2 ions, 1 each of positive and negative, we actually assume that H plus times A minus is actually H plus squared, because we're assuming that that's the same, and this is where we get the square root from. I explain it in more detail in the actual live that we did on it, but I think we don't have as much time today, so if you have a question about that, then do just let me know. What is the effect of temperature on Kc? So I think maybe I'm seeing that a little bit delayed. I've just seen a question on this. It depends on whether the forward or backward reaction is exothermic or endothermic. So an increase in temperature will always favor the endothermic direction. So if the forward reaction is endothermic, increasing the temperature will favor the forward reaction, and that will make more products. More products gives you a larger Kc. If the forward reaction is exothermic, then that means the backward reaction is endothermic. So an increase in temperature will favor the backward reaction. You'll have more reactants than products, and that means your Kc will be smaller. So the effect of temperature on Kc completely relies on whether the forward or backward reaction is endothermic. An increase in temperature will always favor the endothermic direction. I hope that answers your question. Okay, so going back to acids, pH, and buffers. I will go back to this buffer one in a second once we've gone through an example of weak acids, because this is obviously a little bit more complex than the other ways of calculating pH. The thing to just always come back to is the fact that pH is always equal to minus log of H plus. So whatever your question, you've got to find the concentration of H plus in order to find the pH. Okay. Another sort of point to remember, kind of a useful thing to help you to check things or to kind of work out what pHs should be, is that this is kind of the pHs on the acidic side of the scale. pH being in relation, so since pH is minus log of the H plus concentration, we're talking about log base 10. This is a transformation that basically turns something that increases exponentially into a straight line. So if you do maths A level, you may know what I'm talking about. If not, then you may just have to take my word for it, or ask some people who do maths to explain how log works. But basically, it's this table here. What it's saying is, let's start at this point here. If we have an H plus concentration of 1, if you plug in minus log of 1 into your calculator, you're going to get 0. Okay, so if H plus is, excuse me, if the H plus concentration is 1, then you're going to get a pH of 0. If we divide that by 10 and we get an H plus concentration of 0.1, then if we plug that into the pH calculation, that's going to give us a pH of 1. If we divide that by 10, it's going to increase the pH by 1. So every time we divide the concentration of H plus by 10, we're increasing the pH by 1. You divide by 10, increase by 1. So it's in an inversely proportional relationship. That's why we've got pH equals minus log. And then this log means that we're timesing or dividing by 10. So if we go the other way, it's sort of the same thing, but the other way. So here we're timesing by 10, and we're decreasing the pH by 10. We're timesing by, sorry, by 1. Timesing the pH by, timesing the concentration of H plus by 10, decreasing the pH by 1. So there's a consistent and predictable relationship between pH and H plus ions, which you may quite easily be able to see if you study maths, but if you don't, it may not be something that's so obvious. So just make sure you know, underlying all these calculations, you've got ways of common sense checking your answers, and that you also understand that a lower pH means a higher concentration of H plus ions, and an increase in pH by 1 pH unit is actually a decrease in H plus ions of 10 times that. So that's just sort of an interesting thing to remember, and it can be useful in the exams. Okay, I think we've covered most of this stuff, just not in quite as much detail. So I'm just going to flick through a few of these things. Please do feel free to ask questions if there's anything you're not sure about. Yeah, this is basically explaining what I was talking about earlier about weak acids. Because of the 1-to-1 ratio up here of the H plus to A minus, we can assume that the concentrations are the same, and that turns the expression into H plus squared, and that's where we get the square root from. But you can also obviously just learn the equation. I just do recommend trying your best to understand it, because then you don't have to remember as much in the exam. You just kind of have to think about things that you understand. Okay, on to buffers. Got about 20 minutes left, and I do hope to get on to lattice enthalpy as well. So I'm going to try and go through this relatively swiftly. The key thing about buffers, you need to be able to define them as a substance that resists changes in pH. They're usually made up of a combination of a weak acid and its conjugate salt. What that means is, if this is our weak acid, the HCOOH, then the negative, or the acid ion in that, is the HCOO minus. So you've got the weak acid, and we need a salt that contains that same ion. So in this case, the salt is HCONA, and that is going to release the same ion. There are a few other ways of producing buffers, like, for example, from neutralization reactions, but ultimately they produce a combination of a weak acid and its conjugate salt, and that's how a buffer works. So just undo some of that highlighting so you've got the correct color coding now in for this reaction. So we've got these two equations here. The first one is the salt breaking down, dissociating fully into its ions, and then we've got the weak acid that dissociates partly into its ions. If you look at that in relation to the Ka equation, we've got, obviously, you've got the blue, which is the H plus, you've got the purple, which is the HCO minus or A minus, and then the HCOH, which is the red one, highlighted one, and that's your HA from the generic equation. The thing that most people get confused about in this kind of calculation is why we have two HCOO minuses, but we don't have to think about or add up the concentrations of both of them. And ultimately, it's because the concentrations of these two things are always going to be really, really, really tiny, due to the fact that the weak acid doesn't dissociate very much. Whereas because the salt dissociates fully, the concentration of the HCOO minus up on the salt equation is going to be relatively high, significantly higher than the one down here. So when we're looking at finding a value to put in for the HCOO minus ion down here, we need to be looking for the HCOO minus from the salt equation. So if you're given the concentration of the salt, then your HCOO minus or your A minus will be directly from the concentration of the salt. It's only the red stuff on the bottom, the red highlighted thing on the bottom, the HA, your concentration, or your HCOOH concentration, that's given to you by the actual concentration of the weak acid. So how does a buffer actually work? Well, if you add H plus ions to this mixture, then what's going to happen is that the HCOO minus ions from the salt, because there's lots of those, will react with the H plus ions in a neutralization reaction. As long as there's not too many H plus ions added, then those HCO minus ions from the salt are going to basically absorb those H plus ions, and then it's not going to affect the equilibrium here, which is what is going to affect the pH, because we're focusing on, how does this change affect the concentration of H plus ions. So if we add H plus ions, but there's no salt solution, then of course the pH is going to decrease because we've added more concentration of H plus ions. But because we have the salt solution there, the conjugate base ions, the A minus ions, react by mopping up those extra H plus ions that have been added. Of course, if you just keep adding more and more acid, then eventually your A minus ions are going to run out, and obviously eventually the pH will change. That's why we say that it resists the change in pH rather than prevents or stops the change in pH. So if we add OH minus ions, then have a look at what will happen to this combination of reactions. So if we add OH minus ions, okay, then the H plus ions, so here, are going to react with those OH minus ions. But once they react, equilibrium will shift to the right to counteract the change or to replace the H plus ions that are lost. So again, as long as there's not too many OH minus ions added, then any H plus ions which are reacted away by those OH minus ions will be replaced by the shift in equilibrium. And so it's important to understand how that works in terms of explaining how a buffer actually works to resist pH. What happens when you add H plus ions and what happens when you add OH minus ions? How does this combination of two reactions, the conjugate base salt and the weak acid, how does that combination actually help to resist the changes in pH? Okay, I think we're probably ready to move on to the next topic. Okay, so if you're interested in the notes from this live, then please just let me know. Probably the best way to contact me is through DM on Instagram at Boost Revision. I'd be happy to share the notes from this session to help you guys revise. Alternatively, obviously, do think about joining the chemistry clinic, where we've got all of the notes inside the learning platform that we are building there. So lattice enthalpy. First of all, we need to think about some definitions. And actually, I think I've said that, but I've not actually defined lattice enthalpy in the definitions here. So lattice enthalpy is the enthalpy associated with forming 1 mole of an ionic compound from its gaseous ions. So, oh yeah, that's it. I thought I hadn't included it. This is our lattice enthalpy of formation, forming 1 mole of a compound from its gaseous ions. Okay. These other definitions are definitions which basically lead into how we write Born-Haber cycles in order to calculate lattice enthalpy of formation of compounds, because it's not something we can measure practically. We don't generally have gaseous ions floating around that we can turn into compounds and measure the temperature change in that reaction. So we use the Born-Haber cycle, which is basically an extension to the Hess cycle, which looks at a series of other changes that would be needed to go from an ionic compound to its gaseous ions, or vice versa, all based around Hess's law, which means that, which states that the enthalpy change in the reaction will be the same as long as, no matter what the route is, as long as you've got the same reactants and products in the same states. So we'll look in a second at how to kind of draw this extended Hess cycle, but the most important thing, and I can't stress this strongly enough in this topic, the most important thing is to learn your definitions and not just to be able to regurgitate them and write them down if someone asks for definition, but to be able to understand what they actually mean and how to write an equation that matches that definition. So, for example, if I was to write an equation for the lattice enthalpy of formation of sodium chloride, I need to be making 1 mole of that compound, which is sodium chloride, from its gaseous ions, which is sodium and chlorine. With state symbols, we've got gaseous on the left-hand side and we've got solid on the right-hand side. So each of these definitions is not just a definition, but you can actually write an equation, a chemical equation that matches that definition. Okay, so enthalpy change of formation, we've got 1 mole of a compound being formed from its elements in their standard states, and that again is important because now we can write the equation for the formation of NaCl, for example. You can see how this is going to be different to the lattice enthalpy because we're starting with the elements in their standard states, which is this, and to make sure it balances, we want to make only 1 mole of the compound, so we've got to have the half Cl2 there. So you can see in both cases we're making the sodium chloride solid, but in enthalpy of formation we're doing that from elements in their standard states, and for lattice enthalpy we're doing that from gaseous ions. So each definition can also corresponds to an equation. Both of these first 2 definitions are going to be exothermic reactions, because making bonds creates or releases energy, and these both were forming bonds to create the ionic lattice, and so these are exothermic reactions. The next two are endothermic reactions, and this is because we're breaking bonds. Okay, so enthalpy of atomization is when we've got 1 mole of gaseous atoms being formed from an element in its standard state. So for example, if this was Cl2 and we're forming a mole of gaseous atoms, we want to be forming 1 mole of Cl atoms. So we'd do half Cl2 gaseous and then Cl gaseous as well. So we're producing the gaseous ions from the element in its standard state. Okay, ionization energy, you will have come across this in another topic on periodic trends. And again, need to know the definition of it and how to write the equation. So it's 1 mole of electrons is being removed from 1 mole of gaseous atoms to form 1 mole of gaseous 1+ ions. So again, if this was sodium, we'd have sodium atoms, gaseous, turning into sodium ions, gaseous, plus electrons. Okay, you don't need the state symbol on an electron because that's just an electron. So a mole of electrons is being removed from 1 mole of gaseous atoms to form 1 mole of gaseous 1+ ions. So each of these definitions matches a chemical equation. Electron affinity is when 1 mole of electrons is added to 1 mole of gaseous 1+ ions. So this is how you make negative ions from elements or from atoms. Actually, in this case, it is from atoms. So if we've got electron affinity, we've got the chlorine atoms, gaseous, and we're adding an electron to make it chlorine minus ions. Okay, and again, 1 mole of electrons is being added to 1 mole of gaseous. Okay, don't actually think that's quite right. It's 1 mole of electrons is being added to 1 mole of gaseous atoms. I have to gaseous atoms to form 1 minus ions. That's what it's supposed to say. It's supposed to read more like the ionization energy, but basically instead of removing electrons, we're adding electrons. Now the reason we haven't said whether it's exothermic or endothermic yet is because it depends on whether it's the first electron affinity or the second electron affinity. So the first electron affinity is exothermic. Well, I think I had this on the next page actually. Yeah, the first electron affinity is exothermic. The second electron affinity is endothermic. And that's because, again, making bonds is exothermic and breaking bonds is endothermic. You might remember mexo-bendo or bendo-mex. So in the first electron affinity, we're attracting an electron to an atom, and a new bond is being formed. And so that new bond is forming, exothermic and energy is released. You may be able to argue, yes, we're forming a new bond in second electron affinity too. However, because the ion that we're adding the electron to is already negative, there's going to be repulsion between these two things. Negative things repel each other. So it takes energy to overcome that repulsion, and that's why the second electron affinity is actually endothermic. So that's important to remember, because in Born-Haber cycles, you do need to draw the arrow in the direction of the energy change. So a downwards arrow is for exothermic change, and an upwards arrow is for an endothermic change, just like you would do in your reaction profile diagrams. So let's just have a look at some examples for that then. So this would be the Born-Haber cycle for sodium chloride. First of all, focus on this bit on the right-hand side here, where this is our lattice enthalpy. The lattice enthalpy, which we said is negative, is the gaseous ions forming the ionic compound. So each arrow represents a definition, is an equation that represents a definition. Now, remembering what we said about Hess cycle, we want to now go through a series of steps that's going to take us another route in order to form the gaseous ions from the solid compound. And for that, we actually normally start at this line here, because that's our elements in their standard states. So for the elements in their standard states, going to make the compound, as we saw before, is the enthalpy change of formation, another exothermic change. Then we can do an atomization reaction. So we're taking the solid particles of sodium and we're turning them into gases. So that's the atomization of sodium, which is a positive change. And then we've got the gaseous molecules of chlorine turning into gaseous atoms of chlorine. Again, the atomization of chlorine, another positive change, so endothermic change. Then we're going to turn the gaseous atoms of sodium into gaseous ions of sodium, and that's the first ionization energy, again a positive change. And then finally we take the chlorine atoms and add an electron to make the chloride ions, and that's the electron affinity, a negative change. So in order to calculate our indirect route, there's two ways of thinking about it. I actually prefer the second way, but what's most commonly taught is the first way. So we're going to start by looking at this one here. So what this one here is saying is basically the red arrow equals all the blue arrows added up. So the red arrows are delta HF, the enthalpy change of formation, and then the blue arrows are each of the atomizations, the ionization energy, electron affinity, and lattice enthalpy. So this arrow here adds up to the same thing as all of these arrows together. But we're trying to find the lattice enthalpy, so you're going to need to rearrange that equation. And the reason I don't like this method so much is because I think people often make mistakes when they're actually rearranging the equation. And that's, we'd want to try and avoid unforced errors as much as possible. But if you rearrange the equation, you get what I would get through my method, and I'll explain what my method is in a second. So lattice enthalpy equals delta HF minus all of the other things. So minus this, minus this, minus this, minus this. The way that I like to do it, rather than kind of just writing the first equation then rearranging it, is I like to think about it, again, a bit like Hess cycles. I want to go from this point to this point, but the other way. Rather than going this way, we're going to go this way. Okay, so how do we do that? Well, we're going to go against that arrow, against that arrow, against that arrow, against that arrow, and with that arrow. And to me, going against an arrow means we change the sign, and going with an arrow means you keep the sign. So you'll be able to see, hopefully, that we're basically going backwards along this route. This first electron affinity is a negative change, but we're going to go against the arrow. Yeah, So so that's here we go. We've got a negative, we've got a minus the electron affinity, which will actually be a minus, which will give us overall, will give us a positive. Then we've got the first ionization energy, so we're going to minus that, and that's a positive, so minusing that's just going to give us a minus. We've got that. Then the next one is this one, the next one is this one, and then the next one is going with the arrow of the the delta HF, and so that's going to be a positive. So I don't know if it makes as much sense the way I summarize it right there at the end, but it definitely makes a lot of sense to me when I look at it in terms of the indirect route from point A to point B, going this way instead, following the arrows and making sure, to me, I think there's much less error, less potential for error if you go along the arrows and only change the sign if you're going against the arrow. So that's how I would do it. A couple of other examples we've got here, but we don't have time to go through them all. Just remember that if you've got a positive, a 2+ ion, like magnesium 2+, then you're going to have 2 ionization energies to think about, not just one. And then that means you also have 2 negative ions being created here, and you're going to have a whole molecule here. So here you've got 2 ions. Basically everywhere you've got 2 things being formed, you've got to times it by 2, because the definition is for 1 mole, and now you've got 2 moles. So you've got to think about those 2 additional things when you've got something like this, with a 2+ ion and 2 negative ions. Equally, here you've got 2 positive ions and a 2- ion. So you're going to have 2 times the ionization energy, 2 times the atomization energy. And instead of just having the 1 electron affinity, you're now going to have the 2nd electron affinity as well. And this is where we talked about how one of them is endothermic, exothermic, and the second one is endothermic. Exothermic ones where the arrow goes down, and endothermic ones where the arrow goes up. Okay, we're going to finish in a second, but just before we can finish this topic, we've got associated with these Born-Haber cycles, as well as actually just using it specifically just to calculate lattice enthalpy, using those first sets of definitions. You may also be expected to calculate lattice enthalpy using enthalpy of solution or enthalpy of hydration, or to calculate one of these things, if you know the lattice enthalpy. So again, we've got a couple of other definitions: enthalpy change of dissolving 1 mole of solute in water, and enthalpy change of dissolving 1 mole of gaseous ions in water. And that makes a Born-Haber cycle that looks more like this. I kind of think of it as this being the same arrows we had before, with our gaseous ions here and our solid ionic compound there. But now we're kind of doing this on the other side. We're taking the gaseous ions to aqueous ions here, the gaseous ions of the chlorine to aqueous ions there. And then the last bit that's remaining is the solid ionic compound dissolving in water, creating aqueous ions there. So hopefully you can see that this is just a different way, an alternative route to go from gaseous ions to a solid ionic compound. And again, this allows us to indirectly calculate the lattice enthalpy without being able to measure it. Okay, so unfortunately we haven't had time to go over entropy and Gibbs free energy as well. And as I said, look out, in a couple of weeks we're going to have a session specifically on rates, orders of reaction, rate determining steps, basically generally kinetics. So do look out for that. If you have watched this and enjoyed it, then do consider subscribing to the channel. We're going to have more stuff coming out in 2020, lots of stuff coming up this year, this exam season, revision sessions over Easter and going up to the exam period. So do keep an eye out for what's going on. Remember, we also have an Instagram channel at Boost Revision, so please check in and get in contact through that channel too. So if you have been watching, thank you very much for watching. I hope you found this useful. Please do share it with your friends. If you have any further questions, or if you want any of the notes from this session, then please do let me know, and I'll be happy to share them with you. Like I said, on Sunday, we're going to have a similar session to this, but being hosted by Dr. Owusu, who's going to be running through a bunch of organic chemistry year 13 stuff. So keep an eye out for that as well. Thanks very much again. Have a lovely evening and enjoy the rest of your week, and see you again soon.